Paper production evolution. The history of paper production is a profound chronicle of human ingenuity, marking a fundamental transition from an artisanal, biologically constrained handcraft into a colossus of modern chemical and mechanical engineering. Up until the dawn of the 19th century, the creation of paper was an intrinsically slow, labor-intensive process that relied entirely on the recycling of discarded textiles. The transition from this traditional rag-based economy to the mechanized, wood pulp-driven industrial complexes of the late 19th century revolutionized the global dissemination of information. This transformation involved a series of cascading innovations across mechanical engineering, fluid dynamics, and organic chemistry, fundamentally altering the economics of publishing, the nature of industrial labor, and the ecological balance of the natural environment. The pre-industrial ecology of paper, the epoch of the rag. Before the widespread industrialization of paper production and the discovery of wood pulp as a viable source of cellulose, the global publishing industry was entirely dependent on a finite and unpredictable resource: recycled textiles. Period through the 18th century, the foundational raw materials for papermaking were hemp, linen, and increasingly cotton rags. Because raw plant fibers required excessive processing to break down their lignocellulosic structures, it was far more efficient for papermakers to rely on textiles that had already been processed, spun, woven, worn, and washed by human use. Thus, every sheet of paper produced before the mid-19th century was essentially the reincarnated remains of human clothing and ship sails. The reliance on discarded textiles gave rise to an immense, informal, and highly marginalized shadow economy of urban scavengers. In the rapidly expanding metropolises of the 18th and 19th centuries, an underclass of laborers known variously as rag and bone men, rag pickers, mudlarks, and chiffoniers formed the vital foundation of the paper supply chain. These individuals wandered the streets, alleys, and gutters with pushcarts and sacks, collecting discarded items of value. They scavenged not only rags, which were sold to paper mills, but also bones for glue and fertilizer, metal scraps, and glass. The work was filthy, hazardous, and socially stigmatized, yet it was absolutely essential to the intellectual and literary life of the era. Henry David Thoreau observed in 1854 that the fate of the country depended on the kind of man dropped into the street every morning, a profound recognition of the labor that built the literal foundation of the written word. In London, Henry Mayhew documented the desperate lives of the mudlarks who waded through the raw sewage of the Thames at low tide to scavenge, and the toshers who explored dilapidated underground sewers facing constant risks of suffocation and collapse. In New York City, an 1879 report from the New York Herald described a rag shop in the notorious Five Points neighborhood, where women and children worked by the flickering light of a lantern, buried to their necks in heaps of scavenged textiles. Entire families devoted themselves to the trade to survive. An 1853 interview in the New York Times detailed the life of a German female rag picker who supported her disabled husband, her grandfather, and her children on a meager income of just a few coins a day. Despite their critical economic role, rag pickers were often harshly criticized by social reformers, though they occasionally received praise for their humble vocation. Their labor was immortalized in contemporary art, such as Edouard Manet's large-scale painting, The Rag Picker, which elevated the scavenger to the status of a philosopher, reflecting a modern perception of urban refuse workers as vital suppliers to the economy. The chronic shortage of rags was a perpetual bottleneck for the printing industry. As printing technologies improved and literacy rates rose, mills were frequently driven to solicit the public directly for their old clothes. Printers throughout New England routinely published desperate, often poetic advertisements. A famous 1767 poem published by New England printers extolled the virtues of saving rags, noting that rags are as beauties which concealed lie, but when in paper, how it charms the eye. Another widely reprinted advertisement in the North Carolina Gazette boldly assured young ladies that if they sent an old handkerchief to the paper mill, no longer fit to cover their snowy breasts, it might return to them in the form of a romantic letter. The reliance on domestic rag collection was so severe during times of crisis that when Nathan Sellers, a highly skilled American maker of paper molds, joined the Continental Army in 1776, he was quickly discharged by a special resolution of Congress simply so he could return home to make the molds necessary to produce paper for military orders and powder wrappers. Once collected by the rag pickers and sold to middlemen, massive bales of rags were transported to the paper mills. Early colonial mills, such as the Rittenhouse Mill established in 1990 near Germantown, Pennsylvania, were modeled directly on their European counterparts and required proximity to both urban centers for rag supplies and abundant fresh water for power and processing. Upon arrival at the mill, the rag loft entailed entirely women labor. Women and children were employed to sort the textiles by color and quality, a physically exhausting and dust-choked process. The workers, standing for 12 to 14 hours a day, meticulously stripped away buttons, heavy seams, and hooks from the garments. The cloth was then sliced into uniform strips by dragging the fabric across large, stationary, scythe-like blades mounted on the sorting tables. The atmosphere in the rag room was notoriously harsh. Daylight was strictly required, meaning winter hours dictated by the sun, and the air was perpetually thick with lint and dust, leading to severe respiratory ailments among the women. After the sorting and cutting, the textiles underwent a biological retting process. The rags were wetted, pressed into tightly packed balls, and left in enclosed stone vats or cellars to ferment and rot for several weeks. This controlled putrefaction allowed natural fungi and bacteria to break down the tight weave of the textiles and weaken the outer layers of the plant fibers, making them highly susceptible to the subsequent mechanical maceration. The transformation of the fermented rags into a fluid suspension of individual cellulose fibers required immense mechanical force. For centuries, this was achieved by water-powered stamping mills, an arrangement of heavy wooden mallets that rose and fell on camshafts into stone troughs filled with the rags and a constant flow of highly purified spring water. The quality of the water was paramount. Early papermakers quickly learned that water with high iron content would impart a reddish or brownish cast to the paper, while pure calcium-rich water expedited fibrillation and contributed to the archival longevity of the finished sheet. To aid the process, ground chalk or lime was frequently added to the stamper pits to help swell the cellulose and counteract the yellowing effects of the fermentation. The stamping process occurred in 3 distinct stages. In the first set of stampers, the mallets were fitted with sharp iron nails designed to aggressively smash and tear the fermented cloth into a coarse mass known as half stuff. The material was then transferred to a second set of stampers, which were equipped with flat-headed nails to further crush the fibers. Finally, the pulp was moved to a third mill, where the mallets were covered in soft leather. This final stage provided a gentle, repetitive brushing action that fibrillated the cellulose. Fibrillation is a critical concept in papermaking. It involves abrading the outer walls of the cellulose fiber to create microscopic hair-like tendrils. This exponential increase in the fiber's surface area allows for immense hydrogen bonding when the paper dries, yielding a sheet of extraordinary tensile strength and durability. However, the stamping mill was agonizingly slow, incredibly noisy, and highly inefficient. Preparing a single 10-kilogram batch of finely fibrillated pulp could take a stamping mill up to 8 days of continuous, deafening pounding. This severe bottleneck was shattered in the late 17th century with the Dutch invention of the Hollander beater, a machine that fundamentally altered the mechanics of pulp preparation and replaced the stamping mill in most European operations by the mid-18th century. The Hollander consisted of an oblong wooden or metal tub containing a continuous circular water raceway. At a single point along the raceway, a heavy rotating cylinder fitted with sharp metal blades was positioned precisely over a stationary bed plate that also contained metal blades. As the water and rag mixture circulated through the trough, it was drawn by centrifugal force between the rotating roll and the bed plate. Unlike the blunt, compressive pounding of the stamping mill, the Hollander beater applied a severe shearing and macerating action, operating much like a continuous rotary scissor. The clearance between the spinning roll and the stationary plate could be precisely adjusted to increase or decrease the pressure on the fibers. This mechanical efficiency was staggering. A single Hollander beater could produce in one day the same quantity of highly refined pulp that a stamping mill took over a week to prepare. Furthermore, the aggressive shearing action of the Hollander was so effective that the tedious and foul-smelling rag fermentation process was no longer strictly required. However, this industrial efficiency came at a structural and chemical cost. The shearing action of the metal blades tended to chop the cellulose fibers into shorter lengths rather than gently fibrillating them, resulting in a somewhat weaker paper compared to the remarkably strong, long-fibered sheets produced by the leather-bound stampers. Additionally, the constant friction of the metal blades striking against one another introduced microscopic iron contaminants into the pulp slurry. When the resulting paper was exposed to atmospheric humidity over decades, these embedded iron particles acted as catalysts for localized oxidation, leading to the familiar reddish-brown spotting on historical documents known as foxing. With the rags successfully reduced to a fine aqueous slurry known as stuff, the actual formation of the paper sheet commenced at the vat. The pulp was diluted with vast quantities of water and kept warm and agitated in a large circular tub. The formation of the paper was entrusted to a highly skilled artisan known as the vatman. The vatman utilized a mold, which consisted of a rectangular wooden frame stretched with a finely woven wire mesh and a removable elevated wooden boundary frame called a decal. Plunging the mold vertically into the vatman drew it up horizontally, capturing a precise volume of the dilute fiber suspension. As the water immediately began to drain through the wire mesh, the vatman executed a complex, highly practiced multi-directional shaking motion. This papermaker's shake was the most critical physical action in the entire process. It caused the suspended floating cellulose fibers to weave, cross, and interlock in all directions before the water vanished, ensuring uniform structural integrity and equal tensile strength across the horizontal and vertical axes of the resulting sheet. As soon as the sheet solidified into a highly fragile wet web, the vatman removed the decal and passed the mold to a second artisan, the coucher. The coucher expertly inverted the mold and pressed the wet web onto a damp, highly absorbent woolen felt with a rolling motion, cleanly transferring the paper without tearing it. This process was repeated relentlessly, alternating layers of wet paper and felt, until a post of roughly 144 sheets was built up. The entire post was then moved to a massive wooden screw press, where the combined physical strength of several workers was used to subject the pile to immense pressure, expelling the majority of the residual water and forcing the cellulose fibers into tighter microscopic contact. Afterward, the individual sheets were painstakingly separated from the felts by a worker known as the layman. The damp sheets were then taken to the highly ventilated upper floors of the mill, known as drying lofts, where they were draped over animal hair ropes or wooden frames to slowly air dry over several days. Because pure cellulose is highly hydrophilic, untreated paper acts essentially like a sponge. If a quill pen were applied to an untreated sheet, the ink would immediately feather and bleed outwards, rendering the text illegible. Therefore, early paper required a chemical treatment known as sizing to render the surface impermeable. Throughout the medieval period and into the late 18th century, this was achieved through tub sizing. The dried sheets were gathered and dipped by hand into vats of warm, highly refined animal gelatin, which was laboriously boiled down from the hooves, horns, and hides of livestock. The gelatin coated the outer surface of the paper, sealing the pores. The sheets were then dried a second time. The final finishing process was designed to render the surface of the paper exceptionally smooth for the printer or calligrapher. The gelatin-sized sheets were interleaved between thin, highly polished plates of copper or zinc, and the entire stack was passed between heavy iron rollers under immense pressure. This plate glazing process compressed the fibers and gave the paper its final glass-like gloss. Each sheet was then meticulously examined in the salve by female workers, who rejected any imperfect sheets and counted the remaining paper into quires and reams for shipment. This artisanal process produced materials of immense physical beauty and archival longevity, but it was fundamentally restricted by the physical endurance of the vatman and the dimensions of the human arm, rendering it incapable of scaling to meet the demands of a rapidly industrializing society. Pre-industrial milestones in chemical engineering. Before the mechanical automation of the paper web could be fully realized, two critical chemical bottlenecks had to be resolved: the slow process of sun bleaching and the labor-intensive application of animal gelatin sizing. For centuries, achieving white paper required starting with perfectly white rags, which were increasingly scarce, or subjecting the paper to prolonged exposure to sunlight and sour milk, a process that took months. The chemical revolution in bleaching began with the French chemist Claude-Louis Berthollet. Born in Savoy in 1748, Berthollet became a central figure in the emergence of modern chemistry, collaborating with Antoine Lavoisier to devise the modern system of chemical nomenclature. While serving as the director of the famous Manufacture des Gobelins tapestry workshops in Paris, Berthollet applied his theoretical chemical knowledge to the practical art of dyeing and bleaching. In 1785, Berthollet became the first scientist to demonstrate the immense bleaching action of chlorine gas. Recognizing the danger and difficulty of handling raw chlorine gas, he developed a stable, liquid solution of sodium hypochlorite in 1789 at his laboratory in the Javel district of Paris, creating the world's first modern bleaching liquid, famously known as l'eau de Javel. This discovery rapidly migrated to the paper industry. By 1792, British papermakers obtained patents for bleaching rags using Berthollet's chlorine compounds. The introduction of calcium and sodium hypochlorites allowed papermakers to utilize severely discolored and dyed rags that would have previously been rejected, drastically expanding the usable raw material pool. However, the early lack of sophisticated chemical knowledge often resulted in the over-application of chlorine, which aggressively oxidized the cellulose chains, resulting in the production of highly brittle, inferior paper that temporarily discredited the process before more refined, multi-stage bleaching systems were developed later in the 19th century. The second massive chemical leap eliminated the agonizing process of dipping individual sheets into vats of animal gelatin. In 1807, Moritz Friedrich Illig, a German watchmaker working in his father's paper mill in Erbach, published a privately funded monograph detailing a revolutionary chemical process: internal engine sizing. Illig discovered that sizing did not have to be applied to the surface of the finished sheet. Instead, it could be introduced directly into the aqueous pulp slurry within the Hollander beater. Illig utilized rosin, a highly hydrophobic resin extracted from pine trees and composed primarily of abyatic acid. However, rosin alone would not adhere to the suspended cellulose fibers in the water. Illig solved this by simultaneously introducing papermaker's alum, aluminum sulfate, into the beater. The alum acted as a chemical mordant. In the acidic environment of the pulp slurry, the aluminum ions formed complex coordination bonds that precipitated the hydrophobic rosin soap directly onto the surfaces of the individual cellulose fibers. When the paper was subsequently formed and passed over heated drying cylinders, the rosin melted and fused, enveloping the fibers in a waterproof barrier. This alum rosin sizing was incredibly cheap, simple, and crucially, it allowed paper to be sized continuously at an industrial scale, perfectly aligning with the simultaneous invention of the continuous paper machine. However, this chemical triumph harbored a fatal flaw. The heavy use of aluminum sulfate created a highly acidic environment within the internal structure of the paper. Over decades, this residual acid catalyzes the hydrolysis of the cellulose polymer chains, causing the paper to literally devour itself. This alum rosin sizing is one of the primary reasons why books published after the 1830s are highly susceptible to severe embrittlement. The mechanization of the web, the continuous paper machine. The push to mechanize paper production was driven by a confluence of rising societal demands and simultaneous advancements in printing technology. The late 18th and early 19th centuries witnessed exponential population growth, urbanization, and the rise of a politically active middle class, which generated an insatiable demand for reading materials. This demand was facilitated by the industrialization of the printing press. For over 300 years since Gutenberg, the printing press had remained a manually operated wooden screw mechanism. This changed drastically in 1812 with Friedrich Koenig's invention of the steam-powered cylinder press, capable of making 400 impressions an hour, and later with Richard March Hoe's 1844 rotary press, which could output an astonishing 8,000 pages an hour. The blistering speed of steam-powered typography created a massive bottleneck at the paper mill. The traditional vatman, constrained by the physical limits of the human body and the discrete sheet-by-sheet nature of the mold, simply could not produce paper fast enough to feed the roaring rotary presses. Furthermore, the physical size of paper was strictly limited to the largest mold a human being could lift and balance when filled with heavy water and pulp. A mechanical solution was required to produce paper in continuous, endless rolls. The breakthrough occurred in France in 1798. Nicolas Louis Robert, a former soldier and mechanical engineer, was employed as an inspector of personnel at Pierre-François Didot's massive hand papermaking factory in Corbeil-Essonnes, a mill that supplied paper for French currency. Robert became increasingly frustrated by the frequent labor disputes and quarrels among the highly unionized vatmen, couchers, and laymen. Encouraged and financially supported by his employer's son, Saint-Léger Didot, Robert set out to design a machine that would bypass the artisan laborers entirely by automating the sheet formation process. After 5 years of experimentation, Robert achieved a functional design. His brilliant conceptual leap was to replace the static rectangular hand mold with a continuous, endlessly rotating belt of woven wire cloth. A continuous flow of pulp was deposited onto this moving wire, and as the water drained away, a continuous web of wet paper was formed. Robert was granted a French patent for the invention of continuous paper in 1799, and his final model successfully produced long sheets of well-felted paper at the popular 24-inch Colombier width. Robert sold the patent rights to Didot for 27,400 francs, but financial instability during the post-revolutionary period prevented Didot from paying him. Robert eventually recovered ownership of the patent, but never realized any financial benefit from his monumental invention, dying broke and destitute as a primary school teacher in Verneuil in 1828. Recognizing that the turbulent economic climate of France was unsuitable for massive industrial investment, Didot transported Robert's models across the English Channel to his brother-in-law, the English paper mill owner John Gamble. Gamble secured an English patent in 1801 and sought financial backing from the wealthy London stationers, the brothers Henry and Seely Fourdrinier. The Fourdrinier brothers engaged the brilliant British mechanical engineer Brian Donkin to turn Robert's rudimentary concept into a robust commercial reality. Donkin, born in Northumberland in 1768, was a polymath of the Industrial Revolution, eventually collaborating on Charles Babbage's mechanical computer, the Thames Tunnel with Mark Brunel, and establishing the world's first commercial food canning factory for the British Admiralty. Working at his Bermondsey engineering works, Donkin relentlessly refined the paper machine, completing the first successful prototype at Frogmore Mill in Hertfordshire in 1803 and a fully functional commercial version in 1804. By 1810, Donkin had erected 18 of these complex machines across Britain. The Fourdrinier brothers invested a staggering £60,000 in the project, but due to a catastrophic error in the drafting of their patent, they received no royalties from competitors who copied the design, and the brothers were declared bankrupt in 1810. Only Brian Donkin achieved financial security from the endeavor, with his company manufacturing nearly 200 machines globally by 1851. To this day, the flat-wire continuous paper machine universally bears the name Fourdrinier. The engineering brilliance of the Fourdrinier machine lay in its ability to replicate the complex physical actions of the human vatman using continuous rotary mechanics. The machine was divided into several distinct operational zones. In the wet end, highly dilute pulp, often at a consistency of less than 1% fiber to 99% water, was pumped into a head box. The pulp flowed out of the head box through a narrow, adjustable horizontal slit known as the slice, falling evenly onto the Fourdrinier wire, a continuously moving, endless belt of finely woven bronze or brass mesh. As the wire belt carried the puddle of pulp forward, water began to drain through the mesh by gravity. Crucially, to mimic the vatman's interlocking shake, the entire frame supporting the breast roll and the forming wire was mechanically vibrated from side to side. This lateral agitation forced the cellulose fibers to cross and weave before the water drained, ensuring structural strength across the web. As the wire traveled, it passed over a series of rapidly rotating table rolls, or tubes. These rolls supported the wire, but more importantly, as the wire pulled away from the descending curve of each roll, it created a localized hydraulic vacuum on the downstream side of the nip, actively sucking water out of the paper web. Further down the line, the wire passed over a series of stationary suction boxes, which used mechanical vacuum pumps introduced around 1830 to forcibly extract even more water from the solidifying sheet. Finally, the continuous web reached the couch rolls. The wet paper, now possessing enough structural integrity to support its own weight, was peeled off the wire mesh and transferred onto a continuous belt of woolen felt. This felt carried the web into the press section, where it passed between pairs of massive, heavy rollers that squeezed out additional water mechanically and equalized the surface texture of the paper. Simultaneously, a completely different continuous paper-making philosophy was developed by the English paper dealer and inventor John Dickinson. In July 1809, at Apsley Mill, operating directly next door to the Fourdriniers' Frogmore Mill, Dickinson patented the cylinder mold machine. Rather than depositing pulp onto a flat moving belt, Dickinson's machine functioned on a vacuum principle. The machine consisted of a large, hollow, perforated metal cylinder tightly covered in a finely woven wire mesh. This cylinder was partially submerged and rotated continuously within a vat filled with dilute pulp. The internal axis of the cylinder was connected to a drain, maintaining a lower hydraulic pressure inside the cylinder than in the surrounding vat. As the cylinder rotated through the slurry, the pressure differential literally sucked water through the wire mesh into the center of the cylinder, leaving a dense, highly uniform layer of cellulose fibers clinging tightly to the exterior surface of the wire. At the apex of the cylinder's rotation, an endless web of woolen felt passed under a heavy couching roller, pressing against the layer of wet pulp. The wet paper adhered to the felt, pulling continuously off the wire cylinder and exiting the vat through press rollers. The cylinder machine proved exceptionally reliable and competed fiercely with the Fourdrinier for decades. Because multiple cylinders could be arranged in sequence, depositing layers of wet pulp on top of one another, the cylinder machine became the dominant technology for manufacturing thick paperboards and high-security watermarked papers. The cylinder machine was the first automated paper machine to be introduced to the United States. In 1817, amid great industrial secrecy, Thomas Gilpin erected a cylinder machine at Brandywine Creek in Pennsylvania, utilizing plans acquired from London. Gilpin's machine was a marvel, producing a continuous sheet of paper 30 feet wide at a blistering rate of 60 feet per minute. The earliest Fourdrinier and cylinder machines successfully formed a continuous wet web, but the paper still had to be cut into sheets by hand and carried to the drying lofts, leaving a massive bottleneck at the end of the line. This was solved by Thomas Bonsor Crompton in 1820, who patented the tandem dryer section. Crompton, drawing inspiration from the textile industry, added a sequence of large, massive cast iron cylinders internally heated by pressurized steam. The wet paper web, supported by dryer felts, was threaded over and under this array of scalding cylinders, which instantly flashed off the remaining moisture. This innovation allowed the machine to output fully dried paper, entirely eliminating the need for drying lofts and dealing a fatal blow to the handmade paper industry. The aesthetic and security feature of watermarking, traditionally created by weaving wire patterns into the hand mold, was adapted for the continuous machine in 1826 with the invention of the Dandy Roll by John Marshall, an English maker of watermarks, and patented by the paper-making Phipps brothers. The Dandy Roll was a lightweight, hollow cylinder covered in woven wire, which rested gently on top of the wet paper web just before it left the Fourdrinier wire. The roll was not driven by a motor, but was turned purely by the friction of the moving paper web. Raised wire designs attached to the surface of the Dandy Roll pressed down into the highly saturated pulp, which was still 97% water at this stage, locally displacing and thinning the fibers to create translucent impressions at industrial speeds. In addition to watermarking, the Dandy Roll compressed the upper surface of the sheet, equalizing the density and improving the overall formation of the paper. Finally, to replicate the smooth, glass-like finish previously achieved by plate glazing, the end of the paper machine was fitted with a calendar stack. A calendar was a towering vertical array of perfectly smooth, highly polished, solid chilled iron rollers. The dried paper web was threaded continuously through the nips of these heavy rollers. The immense hydraulic loading and friction ironed the paper under extreme pressure, flattening the fibers and producing a remarkably smooth, uniform surface that was ideal for high-resolution printing. The web was then wound onto reels, creating massive rolls of paper that could feed the rotary printing presses. The massive scale of these new paper machines and the immense power required to drive the batteries of Hollander beaters rapidly exceeded the capacity of traditional water wheels. Although water power remained abundant in parts of Britain and the United States, the central hubs of the Industrial Revolution, such as Greater Manchester in the Mersey Basin, became severely overcrowded. A drier 19th century climate further exacerbated water power scarcity, restricting the continuous operation of the mills. To alleviate this geographic dependence and ensure reliable year-round operation, paper mills aggressively adopted coal-fueled steam power. The history of steam engine development, from Thomas Savery's 1698 vacuum pump to Thomas Newcomen's 1712 atmospheric beam engine, was initially driven by the need to pump water out of flooded coal mines. However, James Watt's critical 1764 separate condenser exponentially increased the engine's thermal efficiency. Crucially, Watt and his partner Matthew Boulton later solved the problem of converting the reciprocating up and down motion of the piston into continuous rotary motion. This rotary steam power allowed mills to drive the massive rotational shafts of the paper machines, the heavy iron cylinders of the calendar stacks, and the rapid blades of the Hollanders without relying on a river. Early steam generation relied on massive low-pressure haystack and wagon boilers, essentially gigantic copper or riveted iron teapots heated from below. The transition to high-pressure steam and sophisticated internal flues later in the century allowed paper mills to scale up exponentially, utilizing massive stationary steam engines to power factories that stretched for entire city blocks. Mid-century crisis, the paper famine, and transitional fibers. By 1830, there were nearly 60 paper machines operating in the United States alone, and the technology had spread rapidly across Europe. By 1850, UK paper production reached an estimated 100,000 tons annually. This phenomenal mechanical triumph, however, precipitated a severe and catastrophic raw material crisis. The mechanized mills were devouring linen and cotton rags far faster than the urban populations could discard them. In Great Britain, this raw material crisis was dramatically accelerated by sweeping legislative changes. For over a century, the British government had suppressed the circulation of printed material through the taxes on knowledge, a series of punitive stamp duties, advertisement taxes, and a heavy excise duty on the manufacture of paper itself. Originally imposed in 1712 to fund the War of the Spanish Succession and to restrict the licentious radical press, these taxes kept the price of newspapers artificially high, restricting them to the elite. Following decades of intense political agitation and the defiance of radical publishers who printed unstamped papers, the government gradually relented. The advertisement duty was abolished in 1853, followed by the newspaper stamp duty in 1855. Finally, in 1861, the Chancellor of the Exchequer, William Gladstone, successfully repealed the paper duty, removing the final state-led constraint on production. The repeal allowed paper to be manufactured and sold on continuous reels rather than individual stamped sheets. The explosion in demand was staggering. The price of newspapers plummeted. The Daily Telegraph lowered its price to 1 penny, and its circulation skyrocketed to 140,000 copies a day by 1862. Weekly papers like Lloyd's Weekly News eventually reached circulations of nearly 1 million. The total weekly circulation of London newspapers surged from under 400,000 in 1830 to nearly 2.3 million by 1860. Exactly as the demand for paper reached stratospheric levels, the supply of rags utterly collapsed. The outbreak of the American Civil War in 1861 resulted in a Union naval blockade of southern ports, choking off the global supply of raw cotton. At the time, the South produced 2/3 of the world's cotton supply. The British textile industry, heavily concentrated in Lancashire, was completely paralyzed. Without raw cotton, textile factories shuttered, plunging hundreds of thousands of British mill workers into starvation and unemployment during an event known as the Lancashire Cotton Famine. Consequently, the downstream supply of waste cotton and textile scraps to the paper mills evaporated. The price of rags skyrocketed, threatening to cripple the entire trade print. The paper shortage was felt acutely worldwide, particularly in the American Confederacy, where paper became so scarce that newspapers were forced to print on half sheets, and the destruction of a single facility, such as the 1861 burning of the Pioneer Paper Mill in Athens, Georgia, was considered a catastrophic regional loss. Facing imminent ruin, papermakers desperately experimented with alternative biological fibers to stretch the rag supply. Early industrial stopgaps included agricultural waste. In the United States, straw pulping became widespread following a patent by William McGaw in the late 1820s. Straw was packed into massive spherical iron vessels known as rotary rag boilers. These giant rotating pressure cookers were injected with high-pressure steam and strong caustic alkalis like potash or lime. As the boiler rotated for several hours, the alkaline heat broke down the tough siliceous structure of the straw. While straw provided an immediate source of cheap bulk, it possessed a relatively low cellulose content and yielded a highly brittle, weak paper. It was typically relegated to cheap wrapping paper or blended with recycled manila hemp ropes from the shipping industry to create high-tensile packaging material. The most successful transitional fiber, particularly in Britain, was esparto grass. Esparto, comprising two species of tough perennial grasses, Stipa tenacissima and Lygeum spartum, grew wild in dense clumps across the semi-arid regions of southern Spain and North Africa. In the 1850s, the British papermaker Thomas Routledge recognized esparto's immense potential. At his mills in Eynsham and Sunderland, Routledge perfected specialized mechanical bruising and chemical boiling techniques to extract the fine, flexible cellulose fibers from the tough grass structure. Routledge secured a monopoly on the supply of esparto from Spain, prompting massive media magnates like Edward Lloyd to lease the harvesting rights to 100,000 acres of esparto in Algeria, setting up massive export operations in Oran and Arzo. Esparto grass was a revelation. It yielded a remarkably soft, bulky paper that possessed excellent dimensional stability and was exceptionally receptive to printing ink. It provided a critical, high-quality lifeline to the British publishing industry during the cotton famine and remained a staple of fine British bookmaking well into the 20th century. Yet, esparto grass and agricultural straw were ultimately limited by geography, harvest cycles, and low fiber yields. The definitive, long-term solution to the global paper famine lay in unlocking the world's most abundant source of cellulose, the forest. The wood pulp revolution. The transition to wood as the primary raw material for paper represented the final, total industrialization of the medium. Wood is a highly complex biological matrix. It consists primarily of long cellulose fibers, the structural material desired for papermaking, which are tightly bound together by hemicellulose and lignin. Lignin is a rigid, dark, and highly complex organic polymer that acts as the biological glue holding the tree together. To convert solid timber into a flexible sheet of paper, the cellulose fibers had to be liberated from the lignin, a monumental technical challenge that spawned two distinct technological trajectories: mechanical pulping and chemical pulping. The earliest successful attempts to extract pulp from wood were entirely mechanical, driven by sheer physical force. The process was independently conceptualized and patented in the 1840s by two men separated by the Atlantic: Charles Fennerty, a Canadian poet and inventor in Nova Scotia, and Friedrich Gottlieb Keller, a German weaver in Saxony. Both men were inspired by observing wasps, which construct their paper-like nests by chewing and macerating wood fibers. The mechanical groundwood process they developed was brutal but highly effective. Pulpwood logs were sawn into short bolts, tumbled in massive revolving drums to strip away the bark, and then forced under intense hydraulic or mechanical pressure against the abrasive surface of massive, rapidly revolving sandstone wheels. These grinding stones, often up to 54 inches in diameter, and powered initially by direct connection to water wheels, and later by massive electric motors, physically tore the wood matrix apart. The logs were continually sprayed with water to prevent the friction from setting the wood on fire and to wash the fragmented fibers away from the stone. The grinding action shredded the wood, producing a coarse slurry of highly fragmented fibers and intact fiber bundles. The immense economic advantage of the groundwood process was its spectacular yield, because it merely ground the wood without removing any of the heavy chemical components. It retained over 90% of the original mass of the tree. making it exceptionally cheap to produce. This affordable high-bulk pulp fueled the massive expansion of the daily newspaper industry, allowing publishers to print massive, multi-page editions on inexpensive newsprint. In 1863, the Boston Weekly Journal became the first American newspaper to print an edition entirely on groundwood paper. However, the mechanical groundwood process possessed a fatal chemical flaw. Because it relied purely on physical abrasion, the resulting pulp retained almost all the original lignin from the tree. Lignin is highly photoreactive. When exposed to ultraviolet light and atmospheric oxygen, the lignin rapidly oxidizes, producing acidic compounds. These acids physically attack and cleave the long cellulose polymer chains. Consequently, newsprint and books printed on mechanical wood pulp undergo severe auto-degradation. Within a few decades, the paper turns a dark, burnt yellow and becomes so brittle that it shatters at the touch, a phenomenon that has caused immense, irreversible archival crises for libraries attempting to preserve late 19th century literature. To create strong, permanent, and white paper from wood, the lignin had to be chemically dissolved and washed away, leaving only the pure cellulose. The genesis of chemical pulping occurred in 1851 when Hugh Burgess, an American, and Charles Watt, an Englishman, invented and patented the soda process. Unlike grinding, the soda process utilized high-temperature chemistry to attack the specific bonds holding the wood together. In this process, logs were first passed through heavy mechanical chippers, reducing the solid wood to small chips to maximize the chemical surface area. These chips were loaded into massive iron digesters, essentially gigantic, highly pressurized double boilers. The chips were immersed in a highly caustic white liquor, predominantly consisting of a concentrated aqueous solution of sodium hydroxide, caustic soda. The digester was then sealed and subjected to extreme heat and pressure via steam injection. During the cook, which lasted several hours at temperatures between 130 and 180 degrees Celsius, the caustic soda attacked the ether bonds within the lignin matrix. The strong base cleaved the polymer into smaller alkali-soluble fragments. Once the reaction was complete, a valve was opened and the immense pressure blew the contents of the digester into a blow tank. The sudden depressurization caused the softened wood chips to instantly explode and disintegrate into individual fibers. The resulting mixture was washed in a series of vats, separating the dark, dissolved lignin and spent chemicals, known as black liquor, from the liberated intact cellulose fibers. Because the fibers were separated chemically rather than physically torn apart by a grindstone, soda pulp was significantly longer and stronger than groundwood, and because the lignin was removed, the paper was immune to the rapid yellowing of newsprint. The economic viability of the soda process, however, hinged entirely on chemical recovery. Sodium hydroxide was far too expensive to discard after a single cook. Therefore, late 19th century engineers developed a complex, continuous recovery cycle. The spent black liquor was collected and passed through evaporators to boil off the water and increase its solid organic content. This thick, viscous black liquor was then pumped into large recovery furnaces and incinerated. The intense heat burned away the organic lignin, generating massive amounts of high-pressure steam that was captured to power the mill's machinery. Meanwhile, the inorganic sodium compounds melted and collected at the bottom of the furnace as a molten smelt. This smelt was drained and dissolved in water to form green liquor, an aqueous solution consisting primarily of sodium carbonate. In the final crucial causticizing step, quicklime, calcium oxide, was added to the green liquor. The lime reacted with the sodium carbonate, precipitating out solid calcium carbonate and regenerating the active sodium hydroxide. This reconstituted white liquor was then pumped back to the digesters to cook the next batch of wood chips, creating a nearly closed-loop chemical cycle. While groundbreaking, the soda process had severe limitations. The highly caustic chemistry was extremely destructive to the cellulose yield, and the process was largely restricted to easily pulped, short-fibered deciduous hardwoods like poplar. To efficiently process the vast, untapped stands of resinous coniferous softwoods, such as spruce, hemlock, and fir, and to achieve a pulp that was lighter in color, easier to bleach, and possessed longer, stronger fibers, 19th-century chemists turned away from alkaline bases and explored acidic reactions. In 1866, the American chemist and soldier Benjamin Chew Tilghman invented the acid sulfite process. Tilghman, who had previously experimented with treating straw, discovered that cooking wood chips at elevated temperatures and pressures in an aqueous solution of sulfurous acid and a bisulfite salt, usually calcium or magnesium bisulfite, effectively dissolved the lignin without severely degrading the structural integrity of the cellulose. The fundamental chemistry of the sulfite process relied on sulfonation. The sulfurous acid cleaved the covalent bonds within the lignin, while the bisulfite ions attached themselves to the resulting lignin fragments. This chemical substitution converted the highly insoluble lignin into highly water-soluble compounds known as lignosulfonates, which could easily be washed away from the pure, intact cellulose fibers. The resulting pulp was exceptionally strong, relatively bright even before bleaching, and highly versatile, suitable for fine writing papers, and later serving as the foundation for dissolving pulps used in the manufacture of rayon and cellophane. The preparation of the highly acidic cooking liquor required specialized chemical infrastructure. Mills constructed massive absorption towers. Elemental sulfur was burned in rotary combustion chambers to produce sulfur dioxide gas. This gas was pumped into the bottom of the towers, while a solution of alkaline salts, such as sodium carbonate or calcium hydroxide, was sprayed from the top, percolating downwards over a packed absorption zone. As the gas and liquid flowed countercurrently, the sulfur dioxide was absorbed into the water, creating the potent bisulfite cooking liquor. Implementing the sulfite process on an industrial scale, however, posed severe, almost insurmountable metallurgical challenges. The highly acidic cooking liquor rapidly corroded standard iron and steel digesters. Tilghman initially attempted to overcome this by lining his massive 50-foot rotary digesters with heavy lead plates. However, the extreme fluctuations in temperature and pressure during the cooking cycle caused the lead lining to expand, buckle, and leak uncontrollably, ultimately forcing Tilghman to abandon the commercial development of his patent. The sulfite process was rescued from failure and brought to true commercial viability by the Swedish chemical engineer Carl Daniel Ekman. Between 1871 and 1874 at the Bergvik mill in Sweden, Ekman perfected a magnesium-based sulfite process. Utilizing properly engineered rotary digesters and indirect heating, Ekman established the first commercially successful sulfite mill in the world. Ekman later emigrated to England, opening mills in Northfleet and consulting globally to spread the technology. Following Ekman's success, the sulfite methodology bifurcated into two distinct operational paradigms that dictated mill design for decades. In 1876, the German chemist Alexander Mitscherlich developed the slow cook method. Mitscherlich utilized immense stationary vertical digesters, often ranging up to 65 feet in height and lined with specialized acid-resistant brick to solve the corrosion problem. The Mitscherlich process relied entirely on indirect heating. Rather than injecting steam directly into the acid, steam was circulated through extensive coils of copper or hard lead placed in the bottom of the digester. Because the heat transfer was incredibly slow, a Mitscherlich cook was a gentle, low-pressure affair that could last anywhere from 12 to 30 hours. This prolonged, gentle chemical action preserved exceptional fiber length and produced paper of unparalleled strength, but it tied up capital equipment for days at a time. Conversely, between 1878 and 1882, the Austrians Ritter and Kellner patented the quick cook method. They abandoned indirect coils entirely, injecting live, high-pressure steam directly into the acidic liquor within the digester. This direct steam injection rapidly elevated the temperature to 240 degrees Fahrenheit, reducing the total cooking time to a fraction of the Mitscherlich method. The direct steam injectioning process drastically increased mill throughput and production capacity, albeit at the cost of a slightly lower pulp yield and marginally weaker fibers. By 1900, despite the environmental toxicity of its waste, sulfite pulping had utterly eclipsed all other methods, standing as the dominant force in global chemical paper production. The transformation of papermaking from a mechanically intensive artisanal craft into a continuously operating, highly engineered industrial process marks one of the most significant manufacturing achievements of the 20th century. Prior to the widespread adoption of modern chemical engineering principles, paper was predominantly manufactured through the mechanical grinding of wood or through early sulfite processes, which often yielded brittle fibers with high residual lignin content. However, as the demand for high-strength, durable, and bright paper products surged, the industry underwent a paradigm shift, picking up from the early 20th century with the refinement and global dominance of the Kraft process. Today, modern industrial paper production exists as a highly sophisticated chemical and mechanical engineering marvel. It operates at the intersection of complex carbohydrate chemistry, advanced fluid dynamics, rigorous thermodynamics, and real-time automated control systems. By integrating highly detailed delignification models, sophisticated chemical recovery cycles, precision water removal mechanics, and model predictive control algorithms, contemporary paper mills function not merely as manufacturing plants, but as highly optimized, energy-independent biorefineries. This comprehensive analysis will explore the specific mechanical, chemical, and technological mechanisms that drive modern industrial paper production, tracing the exhaustive process from the initial chemical digestion of raw wood chips to the highly automated quality control systems that govern the physical perfection of the final product. The chemistry of chemical pulping, the Kraft process. The Kraft process, alternately known as the sulfite process, is the globally dominant chemical pulping method, accounting for the vast majority of all domestic and international pulp production. The fundamental advantage of the Kraft process lies in its ability to produce exceptionally high-strength pulp with a low residual lignin content while utilizing a much wider variety of wood species than other methods, including highly resinous species like southern pine and non-wood sources such as bamboo and kennef. The process begins in the wood yard, where raw logs are debarked and chipped. The geometry of the wood chips is critical for uniform chemical penetration. Modern mills utilize chips that are precisely screened to be 12 to 25 millimeters in length and 2 to 10 millimeters in thickness. These uniform wood chips are then transported into massive pressurized reaction vessels known as digesters. Within the digester, the chips are submerged and cooked in a highly alkaline aqueous solution known as white liquor. White liquor is the primary chemical engine of the Kraft process, consisting primarily of active sodium hydroxide and sodium sulfide. The primary objective of the digester phase is delignification, the selective degradation and dissolution of lignin, the complex, naturally occurring phenolic polymer that acts as the glue binding cellulose fibers together within the wood structure. The goal is to separate the lignin without excessively degrading the structural cellulose and hemicellulose carbohydrates that will ultimately form the paper sheet. The chemical separation of lignin from cellulose in the digester is driven by aggressive nucleophilic attack. Under elevated temperatures and pressures, the active ions in the white liquor engage in a complex series of reactions. The most fundamental chemical reaction underpinning the Kraft process is the scission of ether bonds within the lignin macromolecule by nucleophilic sulfide and bisulfide ions. As these ether bonds are cleaved, the massive cross-linked lignin polymer is fragmented into much smaller alkali-soluble molecules. Furthermore, non-phenolic lignin units undergo simultaneous demethylation reactions driven by hydrogen sulfide and methyl mercaptide ions. This demethylation leads to the formation of volatile organic sulfur compounds, specifically methyl mercaptan and dimethyl sulfide, which are responsible for the distinct pungent odor traditionally associated with Kraft pulp mills. As the lignin is fragmented and dissolved, it leaves the solid wood matrix and enters the surrounding liquor, transforming the translucent white liquor into a dark, complex, and highly concentrated solution known as black liquor, which contains the degraded lignin, dissolved carbohydrates, carboxylic acids, and organic extractives. Simultaneously, the harsh alkaline environment within the digester initiate a cascade of complex chemical reactions with the wood carbohydrates themselves, specifically targeting galactoglucomannan, xylan, and cellulose. Understanding these carbohydrate reactions is critical from a chemical engineering standpoint because any degradation of cellulose directly translates to a loss of pulp yield and a reduction in the tensile strength of the final paper. Carbohydrate degradation occurs primarily through a mechanism known as peeling. Primary peeling reactions occur rapidly in hemicelluloses, such as galactoglucomannan in softwoods and xylan in hardwoods, and involve the sequential one-by-one loss of sugar units from the existing reducing ends of the polysaccharide chains. As the digester heats up, secondary peeling reactions are triggered as new reducing end groups are formed by the alkaline environment, allowing further endwise degradation. Fortunately, these destructive peeling reactions are naturally counteracted by competitive stopping reactions. Stopping reactions interrupt the endwise degradation by chemically converting the unstable reducing end groups into highly stable carboxylic acid groups, effectively halting any further loss of sugar units from that specific end chain. Beyond peeling, the carbohydrates are also subjected to alkaline hydrolysis, an alkali-catalyzed process that leads to random mid-chain degradation of polysaccharides. While the highly crystalline structure of cellulose makes it relatively resistant to alkaline hydrolysis, the amorphous hemicelluloses degrade much more extensively through this mechanism. The alkaline environment also induces specific side group conversions. For instance, in both softwood and hardwood xylans, the 4-O-methyl glucuronic acid side groups are converted to hexanuronic acid groups through chemical elimination of methanol. These newly formed hexanuronic acid groups remain attached to the xylan backbone and are highly stable in alkaline conditions, contributing significantly to the total acidic group count of the resulting unbleached Kraft pulp, which later impacts the demand for bleaching chemicals. Given the immense complexity of these simultaneous lignin and carbohydrate reactions, optimizing the digester operation requires advanced mathematical and kinetic modeling. Chemical engineers rely on these models to predict the rate of delignification, control the consumption of expensive chemicals, and maximize the preservation of fiber integrity. Historically, early models, such as those developed by Vroom in the 1950s and Kleinert in the 1960s, relied on macro-level variables like temperature and overall alkali charge to predict cooking outcomes. Later, the Hatton model allowed operators to predict the kappa number, a standardized industry measurement of residual lignin content based on the H factor, a mathematical expression combining cooking time and temperature, and the effective alkali charge. As computational power increased, so did the sophistication of digester models. The three-stage model, refined by researchers like Gustafsson, recognized that pulping does not occur at a constant rate. Instead, it mathematically linked carbohydrate degradation to the distinct delignification rates that occur across three distinct temporal phases: the initial phase, the bulk phase, and the residual phase of the cook. This was eventually superseded by the highly influential Purdue model, which divided the solid wood chips into distinct mathematical pseudo-components: cellulose, xylene, galactoglucomannan, high-reactivity lignin, and low-reactivity lignin. Modern extensions of these fundamental models have reached extraordinary levels of detail. The Christensen extension incorporated the precise dependence of reaction kinetics on the specific concentrations of hydrogen sulfide and hydroxide ions. The Anderson modification expanded the simulation to 12 distinct pseudo-components, utilizing parallel differential equations. To handle the continuous digesters used in the largest modern mills, the Wisniewski extended Purdue model implemented lumped parameter approximations to describe the physical transport mechanisms of mass and energy flow. Advanced simulations, such as the Bartia model, integrate the chemical kinetics with thermohydraulic modeling to account for physical compaction changes within the chip column and dynamic flow rates, while the Choi and Kwon model utilizes kinetic Monte Carlo algorithms to regulate both the kappa number and the microscopic porosity evolution of the wood chips simultaneously. By utilizing these advanced predictive models, modern mills can execute model-based feedback control, precisely arresting the cooking process at the exact moment when lignin removal is maximized, but before catastrophic cellulose degradation occurs. The chemical recovery cycle, thermodynamics, and efficiency. The commercial dominance of the Kraft process is not solely a result of its superior fiber quality, but is fundamentally tied to its chemical recovery cycle. The chemical pulping chemicals utilized in the digester are highly caustic and extremely expensive. Discharging them would be economically disastrous and environmentally catastrophic. The chemical recovery cycle is a sophisticated, closed-loop thermodynamic and chemical system designed to recover approximately 95% of the inorganic pulping chemicals while simultaneously generating immense amounts of thermal and electrical energy from the combusted organic wood waste. This recovery process renders the modern Kraft pulp mill not only entirely energy self-sufficient, but often capable of producing a net power surplus exceeding 100 megawatts, which can be sold back to the public electrical grid. The recovery cycle begins as the cooked pulp is separated from the spent cooking chemicals in a series of brown stock washers. The resulting effluent, referred to as weak black liquor, contains the dissolved organic wood material and the spent inorganic sodium compounds. At this stage, the weak black liquor contains only about 15% dry solids and 85% water, making it far too dilute to sustain combustion. To prepare the liquor for the recovery boiler, it must be vastly concentrated. Modern pulp mills employ massive multiple-effect evaporator trains for this purpose. The industry has largely transitioned from older rising film designs to highly efficient falling film evaporators, which are now the standard. In these systems, the liquor flows downward in a thin film over steam-heated tubes, evaporating the water in sequential stages operating at successively lower pressures and temperatures to maximize thermodynamic efficiency. These advanced large-scale installations can evaporate over 1,000 tons of water per hour. As the liquor becomes increasingly concentrated, its viscosity and corrosiveness rise dramatically. To prevent severe corrosion, modern evaporators utilize specialized duplex stainless steel for any surfaces exposed to black liquor exceeding 70% dry solids. Current operational trends in chemical engineering emphasize ultra-high solids combustion. While historical mills struggled to burn liquor at 60% solids, modern advanced evaporation techniques push the dry solid concentration of the heavy black liquor toward 90% prior to combustion, which dramatically increases the thermal efficiency of the subsequent boiler and significantly reduces sulfur dioxide emissions. The concentrated heavy black liquor is sprayed through oscillating nozzles into the recovery boiler, arguably the most critical and expensive single piece of equipment in a Kraft mill. Modern recovery boilers are monumental thermal engines, frequently exceeding capacities of 5,000 tons of dry solids processed per day. The combustion of black liquor is a complex, multi-stage process that must carefully balance thermodynamics with delicate inorganic chemistry. As the liquor droplets fall through the furnace, they undergo distinct phases: drying, devolatilization, char burning, and finally, smelt oxidation and reduction. In the highly oxygenated upper zones of the furnace, the volatile organic carbon compounds are completely incinerated, releasing massive amounts of latent heat. This heat boils water in the walls of the furnace to generate extremely high-pressure steam. Modern boilers operate at extreme thermodynamic conditions, producing steam at pressures exceeding 8,000 kilopascals and temperatures of 480 degrees Celsius, with next-generation designs aiming for 10,000 kilopascals and over 500 degrees Celsius. This high-pressure steam is directed through steam turbine generators to produce the mill's electricity, while the low-pressure exhaust steam is cascaded back into the mill to heat the digesters and paper machine drying cylinders. Simultaneously, a delicate chemical reduction occurs at the bottom of the furnace. The inorganic sulfur and sodium compounds fall to the floor of the boiler, forming a molten pool known as smelt, which consists predominantly of sodium carbonate and sodium sulfide. To maximize the recovery of the active cooking chemicals, the lower zone of the furnace is intentionally starved of oxygen to maintain a reducing atmosphere. This reducing environment forces the highly oxidized sulfur compounds, such as sodium sulfate, to chemically reduce back into the valuable sodium sulfide required for the digester cook. To prevent devastating atmospheric pollution, particulate matter emissions from these immense furnaces are strictly controlled. Over 95% of all Kraft recovery furnaces are equipped with highly efficient electrostatic precipitators, sometimes followed by wet scrubbers, to capture fine particulates and recycle them back into the liquor stream. The molten smelt continuously flows from the bottom of the recovery boiler through specialized spouts and plunges into a smelt dissolving tank filled with weak wash water. The violent dissolution of the smelt creates a highly alkaline solution known as green liquor, so named because of the greenish hue imparted by trace iron impurities. While the green liquor contains the recovered sodium sulfide, its other primary component is sodium carbonate, which is inactive in the pulping process and must be chemically converted back into active sodium hydroxide. This chemical conversion occurs in the causticizing plant, which operates alongside the continuous lime cycle. The clarified green liquor is pumped into a vessel called a slaker, where it is aggressively mixed with calcium oxide, commonly known as quicklime. This triggers a highly exothermic chemical reaction where the calcium oxide reacts with the water to form calcium hydroxide, which immediately reacts with the dissolved sodium carbonate. This double displacement reaction yields the desired sodium hydroxide, thus completely regenerating the active white liquor for the digester, while simultaneously precipitating insoluble calcium carbonate, commonly referred to as lime mud. To close the chemical loop entirely, the lime mud must be recovered and converted back into calcium oxide. The precipitated calcium carbonate is meticulously filtered out of the regenerated white liquor using advanced disc filtration technology, which has largely replaced older clarification tanks to streamline production and yield higher quality, clearer liquor. The washed lime mud is then fed into a massive, slightly inclined rotary lime kiln. Inside the kiln, the mud is heated to extreme calcining temperatures, driving off carbon dioxide gas and successfully reforming the calcium oxide, which is then cooled and sent back to the slaker to begin the cycle anew. In certain specialized, small-scale, non-sulfur soda pulping mills, engineers may alternatively employ a direct alkali recovery system. This method relies on sodium ferrite chemistry, where sodium ferrite is hydrolyzed with water to produce a highly concentrated sodium hydroxide solution, with the remaining iron oxide being continuously recycled back to the combustor. The incredible energy efficiency of the modern pulp mill relies on treating the entire facility as a singular, integrated thermodynamic system. To achieve this, chemical engineers rigorously apply pinch analysis, a highly advanced mathematical and thermodynamic methodology used to map out exactly where energy can be reused across the facility. A pinch analysis evaluates all the hot streams requiring cooling and all the cold streams requiring heating to calculate the theoretical minimum external energy demand. By analyzing the stream data, engineers identify the pinch point, or the pinch temperature. The fundamental rule of pinch analysis is that any transfer of heat across the pinch temperature represents a thermodynamic violation and a direct waste of valuable steam. For example, in a detailed study of a fully integrated Kraft mill, engineers identified 27 cold streams and 35 hot streams. By establishing stream-specific minimum temperature differences, they calculated a theoretical minimum external heating requirement of approximately 135 megawatts against an actual demand of over 153 megawatts. The resulting 18 megawatt discrepancy represented a massive 12% loss in thermal efficiency, entirely due to non-optimal heat exchange occurring below the pinch point. To rectify these inefficiencies, engineers design complex heat integration retrofits. This involves completely rerouting process streams to ensure that waste heat from one area directly satisfies the heating demands of another. For instance, low-pressure utility steam previously used to heat incoming whitewater or bleaching filtrates is replaced entirely with recovered waste heat from digester liquor cooling streams, stripper condensates, or the hot water and warm water systems. By successfully integrating the thermal networks of the pulping, bleaching, and papermaking operations, mills can lower their energy costs by 15 to 40%, dramatically reduce their reliance on fossil fuels, shrink their carbon dioxide emissions by tens of thousands of tons annually, and eliminate process bottlenecks during capacity upgrades. Modern bleaching sequences, ECF and TCF chemistry. While the Kraft digester removes the vast majority of the lignin from the wood chips, the resulting unbleached brown stock pulp still contains between 3 and 7% residual lignin. This residual lignin is highly colored and must be eliminated to produce the brilliant white paper demanded for writing, printing, and high-quality packaging applications. The primary objective of modern chemical pulp bleaching is to systematically oxidize and remove or modify this residual lignin to drastically increase the pulp's brightness, defined as the percentage of incident light reflected at a specific wavelength of 457 nanometers, without compromising the delicate structural integrity and tensile strength of the cellulose carbohydrates. Historically, the industry relied heavily on elemental chlorine gas as the primary bleaching agent due to its aggressive delignification capabilities. However, the environmental discovery that elemental chlorine reacted with lignin to produce highly toxic, persistent, and bioaccumulative polychlorinated dibenzo P dioxins and furans necessitated a rapid and total technological revolution. Today, modern industrial paper production strictly utilizes advanced multi-stage bleaching sequences categorized as either elemental chlorine-free or totally chlorine-free. Elemental chlorine-free bleaching currently stands as the dominant global standard, utilized in more than 75% of all chemically produced pulp worldwide. The fundamental innovation of the ECF sequence is the complete substitution of elemental chlorine gas with chlorine dioxide as the primary oxidizing agent. While chlorine and chlorine dioxide share a nominal similarity, their chemical behaviors and reaction mechanisms with lignin are profoundly different. The chemistry of chlorine dioxide bleaching relies on its highly selective reactivity. When introduced to the pulp slurry, chlorine dioxide preferentially attacks the free phenolic hydroxyl groups present in the residual lignin structure. This specific interaction initiates the formation of unstable quinone intermediates and actively cleaves the aromatic rings of the lignin macromolecule. This rapid ring cleavage breaks the large, complex lignin polymer into much smaller, highly water-soluble fragments that can be easily extracted and washed away in subsequent alkaline extraction stages. Crucially, because chlorine dioxide functions almost entirely through oxidation mechanisms rather than the electrophilic substitution mechanisms favored by elemental chlorine, it drastically curtails the chlorination of the organic material. This selective oxidation effectively eliminates the formation of toxic dioxins and furans and results in phenomenally low levels of absorbable organic halides in the mill's water effluent. Because chlorine dioxide is so highly selective towards lignin and largely ignores the cellulose carbohydrates, the ECF process allows pulp mills to reach exceptional brightness ceilings while perfectly preserving the maximum viscosity, yield, and tensile strength of the fibers. Totally chlorine-free bleaching represents an alternative chemical pathway that entirely eliminates the use of all chlorine-based compounds, relying exclusively on powerful oxygen-based oxidizing agents. A modern TCF sequence typically begins with an aggressive oxygen delignification stage, followed by advanced bleaching stages utilizing ozone and hydrogen peroxide. Ozone is an extraordinarily powerful oxidizing agent. Its chemical mechanism in pulp bleaching involves direct and violent disruption of the electron-rich aromatic regions of the lignin structure by rapid cycloaddition reactions. This aggressive attack quickly breaks down the chromophores, the specific molecular configurations responsible for absorbing light and imparting color to the pulp. However, because ozone is so aggressively reactive, its application must be strictly controlled and brief to prevent it from indiscriminately attacking and depolymerizing the cellulose chains, which would devastate the strength of the final paper. Following ozone or oxygen treatments, hydrogen peroxide is heavily utilized in TCF sequences. The bleaching effect of hydrogen peroxide is primarily driven by the highly reactive perhydroxyl ion, which is formed through the dissociation of the hydrogen peroxide molecule in an aqueous solution. These perhydroxyl ions selectively attack the conjugated carbonyl groups, orthoquinones, paraquinones, and coniferyl aldehydes present within the altered lignin structure. Through targeted oxidation, these dark, light-absorbing chromophores are chemically converted into colorless, highly stable aldehydes and carboxylic acids, brilliantly whitening the pulp. However, the application of hydrogen peroxide to chemical pulp requires incredibly stringent chemical engineering and process control due to its complex and delicate reaction kinetics. The bleaching must be executed under carefully controlled alkaline conditions. The initial pH of the pulp slurry must be strictly maintained between 10 and 12. This high alkalinity is absolutely necessary to favor the formation of the vital carb anions that serve as the substrates for the oxidation reactions. Yet, if the alkalinity becomes too excessive, it rapidly accelerates the spontaneous decomposition of the hydrogen peroxide, wasting the chemical and decreasing the viscosity of the pulp. Operating temperatures are also elevated, typically maintained between 60 and 80 degrees Celsius, while the pulp consistency is kept high, between 10 and 20%, to ensure the local peroxide concentration remains above critical reaction thresholds. The most significant vulnerability of TCF chemistry is the catastrophic catalytic decomposition of hydrogen peroxide triggered by naturally occurring transition metals such as manganese, iron, and copper present within the wood fibers. If left unchecked, these metals rapidly decompose the peroxide into highly destructive hydroxyl radicals that viciously attack the glycosidic bonds of the cellulose, severely degrading fiber strength and darkening the pulp. To mitigate this fatal flaw, TCF sequences require the rigorous application of highly specialized chelating agents, such as EDTA or DTPA, often executed in a dedicated Q-stage wash. These sequestering agents, along with the strategic addition of magnesium salts and silicates, physically bind to the transition metals, neutralizing their catalytic properties, stabilizing the hydrogen peroxide reagent, and providing critical protection to the carbohydrate polymers. While TCF sequences boast a pristine environmental profile regarding chlorinated compounds, they generally face distinct commercial challenges, including slightly weaker fiber strength, lower overall brightness ceilings, lower pulp yield, and significantly higher chemical and energy costs compared to highly optimized ECF sequences. The paper machine wet end, fluid dynamics, and sheet formation. Following the bleaching plant, the highly refined and brightened pulp slurry, referred to as stock, is pumped to the paper machine. The contemporary paper machine is a colossal, continuous manufacturing apparatus, often stretching over 100 meters in length, designed to transform a dilute suspension of fibers into a dry, impeccably uniform sheet of paper at extraordinary velocities exceeding 2,000 meters per minute. The physical transformation begins at the wet end of the machine, which comprises the highly critical approach flow system, the head box, and the wire forming section. As the stock enters the short circulation loop and approaches the paper machine, it is heavily diluted with recirculated white water to an extremely low consistency. At this stage, the fluid consists of more than 99% water and less than 1% solid fiber. This extreme dilution is absolutely necessary to provide the fibers with sufficient physical space to move independently without instantly clumping together. The primary function of the head box is to take this turbulent pipe flow and transform it into a perfectly uniform, razor-thin rectangular jet that spans the entire massive width of the paper machine. The fluid dynamics occurring within the head box are arguably the most critical variable in papermaking, as they directly dictate the mass formation, the small-scale structural uniformity and basis weight distribution of the final sheet. Cellulose fibers in an aqueous suspension have a natural inherent tendency to mechanically interlock and entangle, forming localized dense clumps known as flocks. If these flocks are allowed to persist as the jet hits the wire, the resulting paper will be severely mottled, structurally weak, and visually unacceptable. To prevent this, the internal geometry of the modern headbox is meticulously engineered to generate intense, highly controlled microturbulence. Advanced mathematical modeling, utilizing hybrid direct numerical simulations and large eddy simulation techniques, demonstrate that fiber flocculation and destruction are fundamentally governed by hydrodynamic forces acting down at the Kolmogorov turbulence scale. As the dilute suspension is forced through the complex tube bank and step diffusers of the headbox, intense shear forces are generated. These forces create prominent streamwise elongated structures within the fluid, which manifest as high-frequency spatial modulations of the fluid velocity. These turbulent velocity gradients induce intense microscopic bending forces on the suspended fibers. As the fibers are violently agitated and forced to bend, the mechanical interlocking of existing flocks is fractured. As the fibers straighten out in the brief moments before they lock together again, they are randomly and evenly dispersed throughout the suspension. The precise convergence angle of the slice lip at the exit of the headbox must perfectly balance the generation of this microturbulence with the necessary fluid acceleration required to orient the dispersed fibers in the machine direction just milliseconds before the jet impinges upon the rapidly moving forming fabric. The high-velocity jet of water and fiber exits the headbox slice and impinges upon the wire section, a continuous, highly tensioned woven synthetic mesh that acts as a moving filtration screen. In modern high-speed industrial operations, traditional single-wire Fourdrinier tables have been largely replaced by advanced twin-wire gap formers. In a gap former, the jet is fired directly into a converging wedge trapped between two moving fabrics. This configuration allows for massive simultaneous dewatering from both the top and bottom sides of the sheet. This bilateral drainage is structurally vital because it minimizes the severe two-sidedness that plagued older papermaking methods, ensuring an isotropic distribution of stress forces, filler particles, and internal boundary layer gradients evenly through the entire thickness of the sheet. The physical mechanics of water removal in the forming section operate through two distinct sequential regimes, filtration and thickening. Immediately upon the jet impinging the wire, the filtration regime begins. A dense mat of fibers begins to build up directly on the surface of the synthetic fabrics, while the bulk of the suspension water is driven forcefully through the nascent porous fiber mat by a combination of kinetic impingement pressure and strategically applied vacuum forces from stationary drainage elements located beneath the wire. The resistance to this fluid flow can be fundamentally analyzed using principles derived from Darcy's law. Formulated by Henry Darcy in the mid-19th century, based on the flow of water through columns of sand, Darcy's law linearly relates the volume flow rate of a fluid through a porous medium to the applied hydraulic pressure gradient and the inherent hydraulic conductivity of the material. However, a wet paper web is not a static column of sand. It is a highly dynamic, highly compressible matrix of flexible fibers. To accurately model drainage on a paper machine, engineers rely on the Kozeny-Kármán equation, an empirical modification of Darcy's law. The Kozeny-Kármán equation predicts the saturated hydraulic conductivity of the paper web, based primarily on the dynamic void ratio of the matrix and the immense specific surface area of the microscopic cellulose fibers and fine particles. As the wire carries the web further down the machine over hydrofoils and high-vacuum flat boxes, the dewatering mechanism fundamentally shifts from filtration to thickening. In the thickening phase, the individual fibers are no longer free to move. The entire flocculated matrix is mechanically compressed by the vacuum forces. This compression causes a severe densification of the surface layers of the sheet. Furthermore, the intense downward flow of water pulls microscopic fiber fragments, known as fines, deep into the matrix, where they physically plug the microscopic drainage channels between the larger fibers. This combination of sheet densification and pore sealing dramatically decreases the hydraulic conductivity of the web, making the removal of the remaining water exponentially more difficult and establishing the ultimate speed limit of the paper machine. Chemical additives, retention aids, and colloid chemistry. Because the initial drainage of water through the forming fabric is so violent, massive amounts of microscopic cellulose fines, highly engineered mineral fillers, and expensive chemical additives would simply wash right through the pores of the wire and be lost to the whitewater system if left untreated. To prevent this catastrophic loss of material and ensure process efficiency, papermakers rely heavily on highly specialized synthetic polyelectrolytes known as retention aids. The application and behavior of these very high-mass, water-soluble polymers are deeply rooted in the complex principles of physical colloid chemistry, specifically DLVO theory. DLVO theory describes the stability of colloidal dispersions by mathematically modeling the delicate balance between the attractive van der Waals forces that pull particles together and the repulsive electrostatic double-layer forces that keep them apart. In the wet end of a paper machine, both the cellulose fibers and the added mineral pigments, such as clay or titanium dioxide, naturally carry a negative anionic surface charge when dispersed in water. Because like charges repel, these particles strongly repel each other, establishing a significant electrostatic barrier that prevents them from naturally agglomerating or adhering to one another. Modern retention systems overcome this repulsive barrier through three distinct molecular mechanisms: charge neutralization, patch flocculation, and bridging. The simplest mechanism, charge neutralization, involves the introduction of simple electrolytes like aluminum sulfate, alum, or low molecular weight cationic polyelectrolytes. These highly positive chemicals adsorb onto the negative surfaces, collapsing the electrical double layer and reducing the repulsive barrier, which allows the attractive van der Waals forces to draw the particles into primary minimum coagulation. However, flocks formed merely by charge neutralization are incredibly weak and are easily shattered by the intense shear forces present on fast-running modern machines. To build stronger aggregates, papermakers utilize the patch flocculation mechanism. This involves dosing the stock with cationic condensation polymers of high charge density and medium molecular weight. These polymers adsorb tightly onto the negative fiber surfaces in flat, localized configurations, creating highly positive macroscopic patches. These positive patches act as powerful electrostatic magnets, strongly attracting the bare, negatively charged surfaces of adjacent particles or fibers, resulting in a robust, tenacious flocculation that can survive moderate shear forces. The most dominant and powerful mechanism utilized today, however, is bridging. Bridging utilizes ultra-high molecular weight polymers, most commonly synthetic polyacrylamides, that can exceed masses of 4 million grams per mole. When these massive molecules adsorb onto a particle, they do not lay flat. Instead, they extend long, sweeping polymer loops and tails far out into the surrounding fluid. These extended tails physically reach past the electrostatic repulsive distance and permanently attach to adjacent particles or fibers, creating an actual physical molecular linkage, a bridge between the solids. To achieve maximum retention efficiency without compromising the uniform formation of the sheet, the most advanced paper machines employ sophisticated dual-component microparticle systems. In these systems, a highly charged cationic polymer is first injected into the stock to induce large-scale bridging flocculation. As the stock passes through the high shear environment of the pressure screens, these massive flocks are intentionally shattered. Immediately afterward, a second component, a high surface area anionic microparticle, such as colloidal silica or finely dispersed bentonite clay, is injected. These tiny, highly negative microparticles rapidly react with the fractured loops and tails of the cationic polymer, tightly cross-linking the polymer chains and pulling the fragments back together into tiny, incredibly dense, and highly stable microflocks. This dual polymer system traps the fine fibers and fillers perfectly in place, while leaving large, open pores in the matrix, drastically decreasing the flow resistance of the water and allowing the machine speed to be boosted significantly, offering profound environmental and economic advantages. The press section, mechanics of water removal and shoe press technology. As the continuous paper web reaches the end of the wire section, it passes over the vacuum couch roll and is physically lifted off the forming fabric. At this critical juncture, the web is still overwhelmingly liquid, possessing a dry consistency of merely 20%. The web must possess sufficient inherent wet web strength to survive this open draw and transfers seamlessly into the press section, where the next phase of dewatering occurs. In the press section, water is no longer removed by hydrodynamic vacuum drainage. Instead, it is forcibly expelled from the sheet through immense mechanical compression. The fundamental engineering goal of the press section is to achieve the absolute maximum possible dewatering mechanically, because removing water via physical pressing is orders of magnitude more economical and energy efficient than evaporating it using heat in the subsequent drier section. Furthermore, achieving high exiting dryness significantly consolidates the web, massively increasing its strength and virtually eliminating the risk of catastrophic web breaks during the transfer to the dryers. The physical mechanics of wet pressing revolve around the precise control of transversal fluid flow through a saturated porous medium. The fragile wet paper web is sandwiched against a highly engineered porous synthetic felt. As this combined matrix passes through the nip formed by two heavy, rotating rolls running under extreme hydraulic pressure, the void volume of the paper sheet is violently compressed. This rapid compression causes the hydrodynamic pressure within the interfiber water to spike drastically. This intense pressure gradient forces the water to flow transversely out of the microscopic pores of the paper and into the much larger available void spaces of the adjacent absorbent felt. The total volume of water that can be successfully expelled during this event is directly proportional to a variable known as the press impulse. The press impulse is mathematically defined as the product of the peak mechanical pressure applied to the sheet and the total residence time, the dwell time that the paper spends inside the nip. In traditional, conventional roll presses, the nip is formed by the contact of two perfectly cylindrical hard rolls. Because two cylinders only contact each other along an incredibly narrow geometric line, the physical length of the press nip is incredibly short, typically only 4 to 7 centimeters. Consequently, at modern machine speeds, the nip residence time is measured in mere milliseconds. To increase the press impulse and remove more water in a conventional roll press, operators had no choice but to drastically increase the applied linear load to increase the peak pressure. However, this approach faced a severe fundamental limitation. If the peak pressure became too extreme, the delicate structural matrix of the paper would literally be crushed and destroyed. This critical physical constraint was entirely overcome by the invention and widespread implementation of the extended nip shoe press. The shoe press represents a monumental leap in paper machine engineering. Instead of relying on two cylindrical rolls, a shoe press pairs a standard, position-stable rotating backing roll with a stationary, hydraulically loaded concave pressure shoe. A highly flexible, durable synthetic polymer press sleeve, such as the NipoFlex roll cover, rotates around the stationary shoe, conveying the paper and the felt through the machine. The concave geometry of the shoe is machined to precisely match the curvature of the opposing backing roll. This elegant geometric matching creates an extended nip that is massively longer than a conventional nip, typically 25 to 30 centimeters in length, an increase of 5 to 7 times the contact area. This vast expansion of the nip allows the press to apply an optimal pressure gradient over a significantly longer dwell time. The press impulse is exponentially increased, forcibly driving out a massive volume of water without ever exceeding the critical peak pressure threshold that causes the fibers to crush. The implementation of shoe presses allows modern paper machines to achieve exiting web dryness that easily exceed 40%. This dramatic increase in dryness provides monumental savings in steam costs for the dryer section, significantly improves the physical consolidation and strength of the web, and ensures phenomenal machine runnability at world record speeds. The dry end, steam thermodynamics and surface sizing chemistry. Upon exiting the press section, the mechanically consolidated web enters the dryer section, the longest and most energy-intensive portion of the paper machine. The primary objective here is to remove the remaining moisture through latent heat evaporation until the paper reaches its final equilibrium moisture content, typically around 5%. The sheet is threaded via automatic pneumatic tail threading devices around a serpentine, multi-tiered series of massive, steam-heated cast iron cylinders. Heat is transferred purely via conduction. High-pressure steam injected into the hollow core of the cylinder condenses against the inner wall, releasing its massive latent heat. This thermal energy conducts through the thick cast iron shell and flashes the water residing in the intimately contacting paper web into vapor. The thermodynamics of the dryer section are highly scrutinized, and chemical engineers rely heavily on pinch analysis to optimize heat integration. Complex cascade steam systems and high-velocity thermocompressors are utilized to continuously recover and recompress the blow-through steam from the higher-pressure dryer groups to feed the lower-pressure groups. Massive air-to-air heat exchangers are mounted in the exhaust hoods above the machine to recover the latent heat from the humid exhaust air, utilizing it to preheat the incoming pocket ventilation air or to heat the mill's process water, strictly preventing any thermal energy from escaping the pinch constraints of the mill. Midway through the sprawling dryer section, once the sheet has been dried sufficiently to absorb liquid, the process is frequently interrupted by the size press. Surface sizing is the continuous application of an aqueous polymeric formulation directly onto the surfaces of the fast-moving paper web. The fundamental objective of the size press is to dramatically improve the physical characteristics of the paper, specifically its stiffness, its internal burst and tensile strength, and critically, its surface strength. By coating the sheet in a continuous film, the sizing solution binds down any loose surface fibers, effectively preventing dusting or linting during the subsequent high-speed offset printing process, which would otherwise contaminate the printing press and ruin the print resolution. Furthermore, surface sizing controls the porosity of the paper, decreasing air permeability and creating a uniform surface that perfectly holds out printing inks, resulting in sharper images and much higher print density. The primary active chemical used in surface sizing is starch, derived from corn, potato, or tapioca. However, native starch in its raw form is far too highly viscous to be applied at high machine speeds. Therefore, it must undergo complex chemical modification or enzymatic conversion on site to reduce the molecular weight of the polymer chains, significantly lowering the viscosity of the solution while maintaining its film-forming capabilities. While older, slower paper machines utilized puddle or flooded nip size presses, where the paper was physically dragged through a deep pond of starch solution before being squeezed between two rolls, this method is highly prone to catastrophic web breaks caused by extreme hydrodynamic wedge forces at high speeds. Modern industrial papermaking has entirely shifted to the use of advanced film presses, often referred to as blade metering size presses. In a film press, the sizing formulation is not pooled against the paper. Instead, a finely tuned mechanical blade where a precision-grooved rotating rod is used to pre-meter a perfectly uniform micron-thin film of the sizing solution directly onto a large elastomer-covered transfer roll. The paper web then passes through the nip between two of these transfer rolls, which simultaneously print the pre-metered film onto both sides of the sheet. Because the film press eliminates the hydrodynamic pond, it drastically decreases web breaks and significantly increases productivity. Furthermore, it allows papermakers to apply sizing formulations with much higher total solids contents, frequently operating in a range of 5 to 18% soluble polymeric matter, which substantially reduces the amount of water introduced into the sheet and vastly decreases the immense thermal energy required to re-dry the paper in the subsequent after-dryer section. To achieve specialized product specifications, modern surface sizing formulations are highly complex chemical cocktails. Papermakers frequently incorporate synthetic water-dispersible film formers like carboxymethyl cellulose (CMC) or polyvinyl alcohol (PVA) to enhance grease resistance and flexibility. They optimize the inclusion of platy mineral particles, such as refined clay or calcium carbonate, which physically fill the microscopic pores of the sheet much more effectively than starch alone, yielding a smoother surface. Furthermore, hexasulfonated fluorescent whitening agents, FWAs, are heavily dosed at the size press. Their high water solubility allows them to diffuse deeply and uniformly into the sheet, absorbing invisible ultraviolet light and re-emitting it as visible blue light, driving the optical brightness of the paper to extreme levels. Internal sizing mechanics, the chemistry of AKD versus ASA. While surface sizing with starch provides strength and binds the surface, it does not make the paper waterproof. Without internal sizing, paper acts like a sponge, instantly absorbing aqueous liquids, which leads to uncontrolled ink bleeding and feathering during printing, destroying image clarity. To impart true liquid wetting resistance or hydrophobicity, modern alkaline papermaking utilizes highly reactive synthetic internal sizing agents, specifically alkenyl succinic anhydride (ASA) and alkyl ketane dimer (AKD). These chemicals are introduced into the wet stock before the paper is formed but they undergo their critical chemical reactions and molecular orientations during the thermal drying process, fundamentally transforming the naturally hydrophilic cellulose fibers into a highly stable water-repellent matrix. The primary intended sizing mechanism for both chemicals relies on their ability to form strong chemical bonds directly with the cellulose fibers. ASA features a highly reactive cyclic anhydride chemical group. Because of the intense ring strain within this cyclic anhydride group, ASA reacts extremely rapidly with the hydroxyl groups extending from the cellulose chains, forming incredibly strong covalent ester bonds. Due to this rapid reaction kinetic, ASA molecules securely attach and orient their long hydrophobic carbon chains outward almost immediately. Consequently, ASA achieves full hydrophobic sizing practically the moment the paper exits the heat of the dryer section, requiring zero long-term curing time, making it the highly favored choice for high-speed sizing operations where immediate water resistance is critical. However, the extreme chemical reactivity of the anhydride ring creates a severe operational vulnerability. ASA reacts violently and rapidly with water to form alkenyl succinic acid, a hydrolyzed byproduct. While traditional sizing theory dictated that this hydrolyzed byproduct was completely inactive and useless for sizing, advanced near-infrared spectroscopy research indicates a much more complex reality. Unbound hydrolyzed ASA can actually provide excellent sizing, but its effectiveness depends entirely on its physical orientation. If the hydrophobic carbon tails are forced to point outward, the paper repels water. However, unbound ASA is highly mobile. If exposed to elevated moisture or the high temperatures found inside a freshly wound roll of paper, the molecules will physically rotate, turning their hydrophilic acid ends outward or migrating away from the surface entirely. This molecular reorientation results in a sudden, catastrophic loss of water resistance, a notorious phenomenon known as size reversion or fugitivity. To prevent this, papermakers must aggressively dose the system with aluminum compounds, which chemically form ALO bridges that rigidly lock the unbound ASA molecules in the correct hydrophobic posture, stabilizing the sizing against reversion. In stark contrast, AKD utilizes a four-membered lactone ring structure. This chemical structure is inherently far less reactive than the anhydride ring of ASA. AKD reacts very slowly with the cellulose hydroxyls to form beta-keto ester bonds. Because its reaction kinetics are so slow, AKD relies heavily on physical spreading. As the paper passes through the dryer section, the solid AKD particles melt. Driven by high temperatures, the liquid AKD physically spreads across the microscopic surfaces of the fibers via surface diffusion, taking the physical form of an autophobic monolayer precursor. While this monolayer spreading mechanism ensures excellent comprehensive coverage, it is a slow process. AKD requires significantly longer reaction times to fully mature and cure. In fact, AKD-sized paper often continues to develop its full hydrophobicity for days while sitting in the warehouse. However, once cured, the AKD bonds are phenomenally stable, providing superior long-term durability and rendering the paper completely immune to the sudden fugitivity and reversion issues that constantly plague ASA systems. Calendering, surface finishing, and printability. Following the final drying cylinders, the completely dry paper web is subjected to calendering. Calendering is a specialized, intensive mechanical compression process designed to consolidate the paper surface, compress the internal structure to achieve a highly regularized caliper thickness, and drastically improve the optical and tactile surface properties, most importantly, smoothness and gloss. The physics of calendering are governed by the simultaneous application of extreme linear pressure, highly elevated temperatures, and carefully controlled dwell times as the paper is crushed between massive rotating rolls. There is a critical technological distinction in modern mills between hard nip calendering and soft nip calendering, each manipulating the physical properties of the paper in profoundly different ways. Hard nip calenders utilize nips formed by two massive, perfectly cylindrical steel or chilled iron rolls, one of which is heavily heated internally with pressurized steam or hot oil. The hard nip is exceedingly effective at crushing the paper web to a precisely uniform caliper across its entire width. This precise caliper calibration is an absolute prerequisite if the paper is destined for subsequent off-machine coating operations. However, hard calendering possesses a significant physical drawback. Because the unyielding steel rolls apply their peak pressure strictly based on the thickest local variations of the web, the hard nip severely crushes the high-density fiber flocks while applying almost no pressure to the low-density valleys of the sheet. This uneven application of pressure creates severe variations in the density of the final sheet, which can lead to disastrous printability issues, such as ink mottling, where the high-density areas refuse to absorb ink while the low-density areas absorb too much. To overcome this fundamental limitation and achieve superior printability, modern paper machines extensively utilize advanced soft nip calendering. In a soft calendar, the heated steel roll is mated against a highly engineered deflection compensation roll that is covered with a thick elastomeric synthetic cover composed of highly specialized fiber-reinforced epoxy resins. As the paper passes through the nip, the intense pressure causes the soft elastomeric cover to dynamically deform, literally molding itself to the microscopic topographical variations of the paper web. This creates an extended, localized nip that applies a perfectly uniform thermodynamic pressure across both the high peaks and the low valleys of the sheet's surface. The result is a profound improvement in printability and visual characteristics. The soft calendar imparts an exceptionally smooth, uniform density and a high gloss finish without severely crushing the internal fiber structure. Furthermore, because the deformable cover extends the length of the nip, it significantly lowers the absolute peak pressure applied to the fibers at any given moment, making soft calendering inherently volume-preserving compared to hard nips. Advanced modern variants, such as the Nipco Flex calendar, leverage shoe press technology to extend the calendering nip even further. By applying optimal pressure gradients over an incredibly long dwell time, these shoe calendars achieve a massive bulk saving effect. They successfully preserve the critical thickness and structural bending stiffness of packaging boards and graphic papers, entirely minimizing surface macro roughness while using high temperatures to achieve a perfect glass-like surface finish. Automation and QCS, the physics of online sensors. The immense speed, massive width, and sheer complexity of the modern paper machine render manual operational control a physical impossibility. A modern machine producing a web 10 meters wide at velocities exceeding 2,000 meters per minute must be strictly governed by highly advanced distributed control systems and specialized quality control systems, QCS. The QCS relies on heavy-duty robotic scanning frames positioned at the extreme dry end of the machine and often immediately before the size press that continuously and rapidly traverse the entire width of the moving web. These scanners deploy a highly sophisticated array of non-contact sensors to build a real-time, ultra-high-resolution topological map of the paper's physical attributes, ensuring that every millimeter of the product meets stringent commercial specifications. The foundational measurements of the QCS are basis weight, moisture content, and ash content, which are captured using highly precise radiological and optical physics. Basis weight The fundamental mass density of the paper per unit area is measured utilizing advanced nucleonic beta ray transmission sensors. These highly shielded sensors house a radioactive isotope source, most commonly promethium-147 for lighter grades or krypton-85 for heavier boards, paired directly opposite a highly sensitive ionization chamber detector positioned on the other side of the sheet. As the stream of beta particles passes through the moving web, they are physically scattered and absorbed by the mass of the cellulose fibers, the mineral fillers, and the remaining water. The exponential attenuation of the beta ray signal is precisely inversely proportional to the total mass density of the sheet. This allows the sensor's microprocessor to calculate the basis weight with flawless laboratory-grade precision in mere milliseconds. To ensure absolute, unwavering accuracy, these sophisticated systems continuously monitor the exact temperature and the mass of the column of air trapped in the gap between the source and the detector, dynamically adjusting their internal calibration algorithms to completely negate the interference of dynamic environmental fluctuations within the hot, humid mill. Simultaneously, the moisture content of the web is measured using incredibly advanced high-performance infrared sensors, which operate purely on the physics of molecular optical absorption. Water molecules possess highly specific vibrational frequencies that cause them to strongly absorb near-infrared energy at specific wavelengths. Modern QCS infrared sensors utilize either transmission or scatter mode reflection techniques depending on the basis weight of the paper. In a state-of-the-art transmission setup, a specialized multi-channel IR detector measures a primary absorption wavelength that is heavily attenuated by the presence of water. Crucially, it simultaneously measures an adjacent reference wavelength that is completely unaffected by moisture, and a third, highly specialized channel dedicated solely to measuring the inherent optical scattering power of the physical sheet itself. By instantly integrating the signals from all three channels, the sensor's advanced microprocessor algebraically isolates the true mass of the water, entirely eliminating the severe optical interference that would otherwise be caused by varying basis weights, heavy ash loading, changes in fiber refining levels, or even the addition of dark carbon black dyes. Ash content, which quantifies the exact amount of inorganic mineral filler, such as clay, calcium carbonate, or titanium dioxide, successfully retained in the sheet, is continuously monitored using X-ray absorption physics. Because inorganic mineral atoms possess a significantly higher atomic number and electron density than the organic carbon, hydrogen, and oxygen atoms composing the cellulose fibers, they preferentially and heavily absorb low-energy X-rays. The ash sensor operates entirely on this differential absorption principle, calculating the exact mineral loading and providing instantaneous feedback to the wet end retention aid chemical systems to ensure the fillers are distributed flawlessly. Furthermore, experimental optical sensing methods are currently making their way into industrial papermaking to provide even deeper quality control. Techniques such as optical coherence tomography, or OCT, utilizing mid-infrared supercontinuum lasers, and terahertz time-domain spectroscopy are being deployed to provide true three-dimensional tomographic non-contact thickness measurements and to detect microscopic subsurface voids and oil contamination without ever touching the web. Model predictive control, automating the machine and cross directions. The massive stream of high-frequency topological data generated by the QCS scanner is utterly useless without a brain to process it. This data is fed directly into model predictive control algorithms, representing the absolute pinnacle of automated chemical engineering. Papermaking process control is mathematically divided into two distinct, highly complex problems: machine direction control and cross-direction control. Machine direction control focuses on minimizing the temporal variation of the mean profile properties over time as the paper races down the machine. For MD control, the MPC algorithm meticulously builds a vast matrix of linear process models that relate multiple manipulated variables, such as the exact position of the thick stock flow valves, the rotational speeds of the massive headbox fan pumps, and the precise steam pressures within multiple dryer sections, to the controlled variables, which are the resulting basis weight and moisture readings provided by the QCS. By continuously solving these complex sets of nonlinear equations, the MD-MPC can accurately predict future process trajectories. This allows the computer to perform highly complex, fully automatic grade changes in a closed loop. When the mill switches production from a lightweight writing paper to a heavyweight board, the MPC optimizes the changes to all MVs simultaneously, calculating the mathematically fastest possible transition trajectory while continuing to aggressively attenuate process disturbances, thereby minimizing the production of off-specification waste. However, the cross-direction control problem is vastly more complex and mathematically daunting. Cross-direction control seeks to mathematically flatten the physical profile of the paper across its entire immense width at any given moment. To do this, it must manipulate hundreds of individual, highly localized actuators, such as automated slice lip jacks spaced every few centimeters across the headbox, individual basis weight dilution valves, and highly localized induction heating zones positioned across the calendar rolls. The CD process is a massive two-dimensional control problem characterized by extreme multivariable interactions, severe input-output off-diagonal coupling, and frustratingly low signal-to-noise ratios caused by the inevitable lateral shrinkage and sideways wandering of the web as it dries. A single physical movement of one headbox actuator will not merely affect the basis weight directly downstream. The fluid dynamics will cause the change to ripple outward diagonally, creating a complex wave response across numerous adjacent zones. If the computer attempts to correct one zone, it risks creating severe defects in the neighboring zones. To master this chaos, advanced control theory utilizes the offline singular value decomposition of the plant's massive interaction matrix, creating highly detailed finite impulse response models that accurately map the complex relationships between the inputs and the outputs. Traditional model predictive control requires solving a quadratic program online, but this is far too computationally expensive and slow for a system with hundreds of actuators operating in milliseconds. Therefore, modern QCS systems employ the robust ellipsoid algorithm, a specialized, highly computationally efficient fast MPC. This advanced mathematical algorithm takes all the rigid physical limitations of the actuators, including the strict minimum and maximum limits, and critically, the severe second-order bending constraints that prevent the physical destruction and snapping of the metal slice lip, and maps them into a high-dimensional ellipsoid. The size of this ellipsoid is optimized continuously online via a lightning-fast bisection method. To ensure absolute robust stability despite inherent model inaccuracies and high process noise, the controller is mathematically programmed to isolate and act only upon the highly controllable singular vectors, completely ignoring poorly defined spatial modes that the model cannot accurately predict. This advanced matrix algebra avoids the need for online matrix inverses or determinants entirely. Consequently, the central processing unit can compute the perfect, optimized, manipulated variable settings for over 200 interacting actuators in under 10 CPU seconds. This incredible synthesis of physical sensors and advanced mathematical algorithms ensures that the paper profile remains flawlessly flat, optimizing raw material consumption, minimizing energy waste, and guaranteeing the flawless structural perfection of the final industrial product.